Hi everyone, welcome back to STR8CHEM. In this video, we're going to look at some problem solving for molar solubility and solubility. A few important points we need to know before we're going to look into a few examples over here. Number one, most of the solubility values will be given in gram per liter. And it's very important for you to remember to change that gram per liter into mole per liter. Important point number two, must always use a balanced equilibrium equation. Without a balanced equilibrium equation, you cannot write the correct KSP expression. And then the next important point that you need to remember, we will be using the ICE table to calculate the molar solubility or to get the value of KSP. Remember, because we are dealing with equilibrium equation, thus the ICE table will be essential. The next important point, number four, is the flowchart to outline the steps involved in calculating the solubility for slightly soluble salts compound from the KSP value, and maybe if you get the solubility of compounds in gram per liter, and then if the question wants you to find KSP, we're going to use this flowchart. So how does it work? If the question gives you the KSP value right here is given, and then the question wants you to find maybe solubility, or perhaps the question wants you to find molar solubility. The first thing you need to do is you need to get the value of concentration for cation and anion from KSP value. Then you're going to use the ICE table to find the concentration of the cation and anion. Remember, when you dissolve the slightly soluble salts, you will get the cation species and anion species. So if you want to find the solubility of the compound or the salts, or maybe even the molar solubility, and the KSP value is given to you, from the KSP value, we're going to use the ICE table to find the concentration of cation and anion. And then from here, you're going to move on to finding the molar solubility. And from the molar solubility, we should be able to work out the solubility of the compounds. Remember, molar solubility is mole per liter and solubility is gram per liter. Different way of expressing solubility in solubility equilibria. We can do the opposites if we want to find KSP value when the question gives you perhaps solubility, or the question gives you molar solubility. What we can do is we can go backwards in terms of the flowcharts. The question gives you solubility, and therefore we can go backwards like this. So you can convert solubility into molar solubility, and from molar solubility, we can use the ICE table to find the concentrations of cation and anion. And from the concentration of cation and anion, we can use that information to find the KSP value. This is very important flowchart. Therefore, try to use this method of thinking in order for you to solve the problems regarding to molar solubility and solubility. Let's try one example over here. This is the first example we're going to try. As usual, before you want to do anything, it's better for you to identify what the question wants so that you would be able to know where you are headed and what sort of calculation tools you need to be using. The question wants you to determine the solubility product KSP of lead sulfates. So this is what the question wants. If you relate that with what we have talked about the flow chart just now, over here, the question wants you to determine the solubility product, which is this right there. So that is what the question wants. And to get to this point, you need to be using the concentrations of cation and anion of lead sulfates in order for you to find the KSP. Now, what does the question gives you? When you read the question further, the question gives you the solubility in water at 25 degrees Celsius, 4.25 times 10 to the power of negative 3 gram per liter. And that is, this is what the question gives. Okay? To get what the question wants. To get from solubility of compound in gram per liter to KSP, first you have to change this into molar solubility. And then from molar solubility, we're going to be using the ICE table to find the concentrations of cation and anion. And from here, we should be able to work out the KSP value. Remember, when you try to deal with this, we're going to be using the ICE table. Now, the first thing we need to do here is to convert solubility of compound in terms of gram per liter into molar solubility of compound, mole per liter first. So to find molar solubility of lead sulfates, we need to find out what is the molar mass of lead sulfates. The molar mass of lead sulfate is plus, so that is the molar mass for lead, plus the molar mass of sulfur is 32.1, plus molar mass of oxygen times 4, you'll get 16 times 4, and the molar mass is about 303.3 gram per mole. So that is the molar mass, and you should be able to get 1 mark for that. And to find molar solubility, the formula is this. So the formula to find molar solubility is to take the solubility given to you, divide by the molar mass. That is why we need to find the molar mass of lead sulfates in order for you to get the molar solubility from solubility. The given solubility is 4.25 times 10 to the power of negative 3 gram per liter. That is given to you, and we want to work our way towards the molar solubility. And to do that, we need to find the molar mass, and we have found it. And we're going to use this formula to find molar solubility. And Once you've done that, you get something like this. So 4.25 times 10 to the power of -3 gram per liter, this is given to you. Divide by the molar mass that we have worked out just now. And we should be able to know what is the molar solubility of lead sulfate, which is so you get 1 mark for this and 1 mark for the formula that you have used on top. Now, so we have done this, so we have done that one. Now, from here, we need to move forward towards finding the concentration of cation and anion through the utilization of ICE table. We have found what is the molar solubility just now, right there. And we're going to use this value of molar solubility into your ICE table right here. Remember, important point number 2, if we go back to the important point that we have talked about just now, it is essential for you to use the balanced equilibrium equation because we need to write the correct KSP expression from the balanced equilibrium equation. So in the ICE table that we have made right here, you have to make sure that the equilibrium equation you have on top is balanced. Now I have a balanced equilibrium equation, therefore we're good to go. But before we're going to proceed with filling in the ICE table, for this kind of problem solving, it's quite special because the ICE table will be written together with the statement on top here, where we're going to be letting X to be equal to the molar solubility of lead sulfates. Remember, the molar solubility is this, we have found out just now. And then we're going to make this statement together with the ICE table, and you will know later why. So I'm going to highlight that. Then you'll know this is a very, very important step in which you're going to be letting X equals to the molar solubility of lead sulfates. Okay. So when you look at your balanced equilibrium equation, we can see that lead sulfate is in solid form. And we will be able to ignore that because the concept that we have learned about ICE table and equilibrium constant, solid and liquid, will not going to be part of the ICE table and also the equilibrium expression. Same goes to KSP as well. So this solid will be ignored and we will be just focusing on the aqueous species that we have on the product side. Okay, so the initial molarity of your ionic species, your cation and anion right here, obviously will be none in the beginning. But what about the change? Remember, these are products, and change, we always going to be expressing that in terms of X. So the change now is positive X and positive X. Why positive? Because they are being made as products. So they will be increasing in volume or concentration. And why X here? Because you have 1 mole of Pb2 plus cation being produced. And we have 1 mole of SFSO4 2- being produced. This is the reason why you need to ensure you have a balanced equilibrium equation so that you will be able to write the correct change for this part right there. Now, what about the equilibrium? Remember, 0 plus x, you would get x, and then 0 plus x, you would get x as well. So by writing this correctly, you get 1 mark for that section, you get another 1 mark for this section, 1 mark for that section. Also, you will get 1 mark for the correct balance equilibrium equation. And sometimes this statement over here would have another 1 mark. So do remember to always write the let X equals to molar solubility of your compound. So moving forward from the ICE table that we have done here, what can we do is we're going to write the KSP expression. Okay, so the KSP expression would be like this. So this is the KSP expression in which you have the concentration of Pb2 plus times with the concentration of SO4 2 minus. And by writing that correctly, you would get another 1 mark for the correct KSP expression written. By substituting the X value inside, you have this one is equals to X, as you can see over here. Molarity of Pb2 plus at equilibrium is X. Molarity of SO4 2 minus at equilibrium is equals to X. So you're going to put X inside. You would be able to write it like this. Okay? So you're going to get X squared. Why X squared? Because this one is X and that one is X. Now, when you look at the X expression right there, this is what we have done on top. So this is the reason why you need to write this statement, because this is the assumption in which we're going to be letting X as the molar solubility of lead sulfates. So by writing this, we know that X is this X, and we have assumed that the molar solubility is X, and the value of molar solubility is this, the one that we have worked out. And we can plug in that value in here. Okay, so that is the value of molar solubility of lead sulfate that we have got right there. So what I did here, I just plugged in the value and I would be able to get my KSP value in the end. So by getting this KSP value, you would get another 1 mark. Okay, so when you go back to the sequence here, now we have done, you've got this, and finally you would be able to solve what the question wants. Let's have a look at another example. The example right here wants you to find the solubility of silver iodide, okay, AgI, in aqueous solution in moles per liter. So we need to find the solubility of AgI in moles per liter. That is molar solubility. So the question wants now, the question wants you to find molar solubility. Why is it molar solubility? because right here it's quite clear that the question wants you to find moles per liter solubility. And the question gives the KSP value 8.3 exponent negative 17. So this is what the question gives. If we're going to relate that with the flowchart that we have done just now, question gives KSP. So we have, this is what the question gives. And then the question wants you to find this. Okay. This is what the question wants you to find. And to do that, from KSP value, you have to work your way towards the concentration of cation and anion. And yes, we're going to be using the, okay, for this, we're going to be using the ICE table. So you're going to be using ICE table for this. So once you have found this, we should be able to find out what is the molar solubility of compounds as what the question wants you to get. Right. So we're going to go towards the ICE table because the question gives you KSP value. So we're going to be using that one to find the concentration of cation. So that's why we're going to start with the ICE. So here we have the ICE. Don't forget to write the balance equilibrium equation on top for AgI solid, and don't forget the phases. Without the phases, you wouldn't be able to get your 1 mark. So by writing the balance equation, you get 1 mark, and do remember to write your phases is very important. And you need to write this statement on top. Let X equals to the molar solubility of AgI. This one also will be giving you, okay, very, very important. So you get 1 mark right there. Okay. And do remember that for solid, we're going to be ignoring that. And in the beginning, we don't have this being made yet. And the change plus X, these two are products, 1 mole, 1 mole. And at equilibrium, you have X, because 0 plus X, you will get X. Okay. So this is the ICE table that you should be getting for this problem. So by writing the correct ICE table, you would be able to get 3 marks for the whole thing here. 1 mark for that section, 1 mark for the change section, and 1 mark for the equilibrium section. Okay, so what do we need to do next? Now we have found out the concentration of cation and anion through ICE. We have done this, and we're going to move forward to molar solubility. And how do we do that? You do remember the question gives you the KSP value, and we can use that and we can compare with what we have over here. So the KSP for the examples that we have is written like this. So this is the KSP expression for what we have right there. By writing the correct KSP expression, you would be given another 1 mark. And do remember that at equilibrium, the concentration of Ag plus and I minus is equal to X and X. Therefore, we can write the KSP now as X times X squared. And we can use this to compare with the KSP value that has been given in the question. So the question gives the KSP value 8.3 times 10 to the power of negative 17. Okay, so the KSP value given is 8.3 times 10 to the power of negative 17. And as you can see over here, KSP is equals to X squared. So you have X squared to be compared with 8.3 times 10 to the power of negative 17. And thus X is, the value is about 9.1 times 10 to the power of negative 9 molar. Therefore, the molar solubility of AgI is 9.1 times 10 negative 9 molar. Okay, so you would be able to get 1 mark for this, and then you would be able to get 1 mark for putting that into X right there. Okay, so we have assumed this X just now. So by finding the value of X, we have assumed that to be equals to molar solubility. This is the reason why this piece of information that you're going to write together with your ICE table, let X, will be very important, because from there we would be able to justify why the molar solubility of your compound will be equivalent to the value that you have worked out through the step right here. Okay, so we're done with that one. So if you go back to your flow chart, so we have done this. Okay, now, okay, for the final example I have for this video is when we need to find the solubility of FeOH2 iron hydroxide in terms of gram per liter, as you can see right there. So this is what the question wants, and it wants you to find the solubility. Given the molar solubility product KSP, which is 4.8 times 10 to the power of negative 14. This is what the question gives. And if you relate that with the flowchart that we have just now, the question gives KSP, which is that. So this is what the question gives. And the question wants you to find solubility, and solubility is right there. So this is what the question wants. To get from Ksp to solubility of compound in gram per liter, we have to move from Ksp to find concentration of cation and anion. And remember, for this, we're going to be using the ICE. And then we're going to move towards finding molar solubility of compounds. And finally, we will be able to find the solubility of the compound. That's why the flow chart here is super important for you to remember and to use to solve the problems regarding to molar solubility, solubility, and solubility products. Okay, so we're gonna proceed with the construction of ICE table, as what we have seen here from the KSP, what the question gives. If we gonna move towards solubility, we need to go through the concentrations of cation and anion first by using the ICE table. So this is the ICE table that we have. Remember, write down the balance equilibrium equation on top. This is the balance equilibrium equation. And then the statement let X equals to molar solubility of iron hydroxide is very important. By writing that, you get 1 mark. By having the balance equation, you get another 1 mark. And do remember, for the solid phase right there, it would be ignored. Initially, we don't have this being made yet, so that one would be 0. And the change plus X plus 2X, 1 mole plus X, 2 mole plus 2X. Thus, at equilibrium, the concentration of Fe2 plus is X, according to the ICE table. And for the OH minus, it would be 2X. You get 1 mark for this section, 1 mark for this section, and another 1 mark for that. So from the ICE table that we have produced, we should be able to proceed to the next step. So we have done this. Now we're going to be moving forward towards molar solubility. That's why we have this section here. Remember to write down the KSP expression correctly. For this equilibrium reaction, the KSP expression should be written like this. So by writing the correct KSP expression, you get another 1 mark. So what we need to do next, we're going to be plugging in the X value, and then also remember this one is OH minus, so what is the value? It's 2X. So you're going to put 2X to the power of 2, and thus you'd get 4 x cubed. By getting that correctly, you get another 1 mark. Now we're going to compare with the value of KSP given. So the question gives the value of KSP is 4.8 times 10 to the power of negative 14. So you're going to compare that with the 4x cubed and you should be able to calculate that by using your calculator. This one you should be getting about 1.2 times 10 to the power of negative 14. This is when I move forward to the other side. And then to solve this value of x, simply use your calculator. You should be able to get x equals to 2.3 times 10 to the power of negative 5. So the molar solubility of FeOH2 is 2.3 times 10 negative 5 molar. Don't forget your units. It's very important. For after you have got that one, you will be granted 1 mark for that. Now, so we're done with this. Next, we're going to move from molar solubility and we're going to move to the solubility of compound in gram per liter. And how do we do that? We have this value already. Okay, to find the solubility, first we need to find out what is the molar mass of FeOH2, because we do know that the formula is as such. So that is the formula, molar solubility, that we have found out here. We would be multiplying that with molar mass. And when you get the molar mass in this step there, you should be able to solve for solubility. So the molar mass is, iron is about 55.9. That is the molar mass for iron. And then plus with 16 plus 1.0 times 2, you'd get the molar mass 89.9 gram per mole. So that is the molar mass for iron hydroxide. You get 1 mark. And we take this value, you're going to multiply with the molar solubility of which we have worked out right there. And this is the solubility of FeOH2. That's the question wants. 1 mark will be granted for that, and 1 mark will be given for the final answer.